Hello, calculus fans! Alright, we're going to talk about a new application of derivatives. This is called linear approximations. So we know that if you draw a curve and then you draw its tangent line at some point, the curve is actually really close to its tangent line near that point. In fact, if you used your calculator to zoom in on the graph of the curve and of the tangent line, you would see that the graph looks more and more like the tangent line the closer you get. So as you zoom in, you can't tell the difference between the curve and the tangent line. So we're going to use this notion as the basis for a method of approximating a function. Let's suppose that we have a function, and we'll say that it's easy to compute f of a, but possibly not so easy to compute f of x when x is near a. So in order to approximate the function, we're going to use the linear function whose graph is the tangent line of f at the point where x is equal to a. So instead of using the function, we use the tangent line to approximate the values of the function. Let's take a look at a picture of what we might have. So this picture illustrates the concept pretty nicely. Let's say that you have a function, y equals f of x, and then you pick a point, a, f of a, and you make a tangent line. So the original function is the one in blue, the tangent line is the one in red. When you're very close to this point of tangency, you should be able to see that the curve is really close to the function. So as long as we don't stray too far from this point, x equals a, as long as we're not too far away from that, then the y values along the line will be very close to the y values along the curve. So let's take an equation of the tangent line to the curve y equals f of x at x equals a. And we know exactly what that looks like. We've done this many times now. This is an equation of the tangent line. Y minus f of a is equal to f prime of a times x minus a. So the thing out in front here is the slope, and then you have the x value of the point of tangency and the y value of the point of tangency. And we've done this enough times that we're pretty used to this. Now I just want to rewrite this a little bit. We didn't really do anything special. We just take this term and move it to the right-hand side. And so now we have a new equation, but it's really the same equation, just rewritten in a slightly different way. So if we use the picture as a basis for what we're doing, we can approximate the function f of x using this linear function. So the approximation looks like this. F of x is approximately equal to f of a plus f prime of a times x minus a. Now this approximation has a name. This thing is called the linear approximation, or you can just call it the tangent line approximation of f at a. So if we make this linear function, this thing here, this linear function has a name. It's called the linearization of f at a. The term we'll use most often is this term here, using a linear approximation. You take some function and approximate it with its tangent line at some point. Now in Calculus 2, we're going to develop somewhat more sophisticated approximation techniques. The linear approximation that we've just talked about will be an example of what's called a first-order Taylor polynomial. And we'll do things with second-order and third-order Taylor polynomials where we'll match up higher-order derivatives. But for Calculus 1, we're just going to mess around with the linear approximation, this first-order approximation. Okay, that's all for now.